Nice to meet you all. Thank you very much for the invitation. I'm very glad to be here. So I wanted to talk today about a shift that happened in the tabular machine learning community, which is the emergence of tabular foundation models that are actually very performant and that outperforms our beloved Tune 3 models. So during the next 20 minutes, I try to cover 5 topics. The first one is remember why tabular machine learning is still an important problem and why it is still a modern research problem. After that, I try to make a deep dive on tabular foundation model and explain what it's actually and how it is built and around which components it works. After that, I will showcase the performance of tabular foundation models against tree-based models, thanks to a new tabular benchmark that we are releasing soon, that is called TabBench. And then a little bit of advertisement for our new API to access in a very efficient and practical way our TFM model, Seldon. And finally, we'll have a discussion about the limitation of TFMs and all the work that remains to do. So to begin with, why tabular machine learning is still very hard and why is it still a very exciting research problem? Well, the first reason is that the tabular modality is very awkward. It's the only modality that groups so many sub-modalities. Each columns can be numerical value. It can be categorical value with high cardinality, low cardinal ones. That can be encoded in strings or numbers. It can contain some strings, even free text. That's the only modality that actually have a lot of missing information. And it's a modality where when something is missing, it's actually information. There is no notion of locality or translation invariance or whatever sequence order in a table. You can permute the columns and the rows and the information will stay the same. And on top of all these specificities, tables can be highly multimodal. It can contain like URL to website, images, video, free text, numbers. And it does that with all kinds of volume. So to give you an idea, we have clients with only a few dozen of rows and other clients that have like billions of rows. And on top of all of that, the way your machine learning model will handle this data is really dependent on the preprocessing, so on the way that you encode all of that data. During a very, very long time, people has observed that tree-based model was way better than deep learning models. A few years ago, there was a kind of a consensus in the research community that say, okay, deep learning models are not very good on tabular data, and that's due to some structural causes in the architectures that we use. People said, okay, MLPs are very smooth, they are very sensitive to uninformative features. The rotation invariance that you have natively in a table is something that is very problematic for MLPs. So all of that reasons led to a decade of predominance of three tree-based models that are XGBoost, LightGBM, and CatBoost. And basically, every production model that handles tabular data will like always be these models. Obviously, when ChatGPT emerges, a lot of people thought, oh, wow, generative AI will solve tabular case. But actually, that's not the case at all. And the two main reasons are that so tokenization is a real issue. So that's what you said, Anton. And standard tokenization in LLM actually like destroy all the information that you can have in a table. And it has the wrong learning objective as well. It is not optimized at all to make pertinent prediction on tabular data. And obviously, it will be way more too costly to use an LLM to do a prediction on a table. Despite all that, some people try to make it work. So you have TabLLM, Lift, Tabular 8B that are very competitive, but only on a very few shot regime, which is kind of obvious because it benefits from the in-context learning of LLMs. A few years back, Müller and team proposed a new way to train transformer on tabular data. So basically, their idea was instead of training one model for one dataset over a distribution of sample, they proposed to train one model on a distribution of datasets. So in this framework, one dataset is actually one sample for the model, and it performs a prediction on all the samples from this dataset in one forward pass. So that is equivalent of doing the prediction of the posterior distribution of the given dataset. And 2.5 years later, all models that are trained on this new framework, which is the prior fitting networks, actually beat all tree-based models, even tuned ones, on very, very broad academic benchmarks. So we are beginning to see the same kind of trajectory that we saw in NLP and in vision, and it's happening in tabular data. So let's deep dive into what a tabular foundation model is. So as I said, it was introduced 2 years ago, and the idea is really to pre-train one model over a distribution of numerous datasets. And the task for which we optimize the model is an in-context learning task. So the model will have some samples that are labeled and some samples that are not labeled. And the game is to predict, obviously, the samples that are not labeled. During 3 years, a lot of actors have proposed different models. So it's a community that is gaining a lot of traction. And the first surprising thing that you can see is that models, well, tabular foundation models are actually quite small with respect to what we know from LLMs. And that is due to the training task that is used. Since we do in-context learning tasks, there is no memorization effect. So we don't need very huge network to make it work. TFMs are built around 3 main pillars, which are the prior distribution, so the distribution of datasets that is used for the pre-training. The second one is the architecture itself, which is how do we actually implement the model. And the final one is a context, so what kind of labeled sets I present to my TFM when I want to make an inference. So let's begin with the first one. Actually, we discovered that the definition of the prior is the thing that is the most important in the final performance of the model. So some team has tried to propose priors that are based on real tables, but actually it doesn't work very well. The thing that works the best is to use the synthetic priors. So that can sound quite surprising at the beginning, but again, since we are doing in-context learning tasks, we don't need to see a lot of real marginal distribution of features or whatever. What we need is to see a very broad variety of patterns between features and targets, because we are learning the model to learn a behavior from a context. To give you some idea on how many datasets do we need to do training, today when we train SOTA TFMs, we use something around 100 million of synthetic datasets. And the way we design these datasets is more like a black art from now than science, because it's something that is very empirical and that we don't control very well. The first technique that is used, that has been used to develop these priors, was to design some DAGs based on a multi-layer perception. So what you do basically is that you initialize randomly an NLP. So you set up a random number of layers, random number of hidden states. You sample a lot of activation between the layers that are randomly applied. Then you put some randomness at the input of the MLP, and you sample some activations along the MLP. And these activations will become one table. And you do that 100 million times during the training. That's a very efficient way to design very broad prior. And you can even bring more diversity by replacing the perceptron layer by a random tree that is fitted on random noise. The evolution of this type of priors is to remove the MLP part and directly generate several random DAGs. And the way we do it is that we generate DAGs with like 32 nodes, and each node will be a vector, and we will create random function between nodes in the DAG, and among each node, you apply random transformation within the vector, and when you perform the sampling to create a synthetic table, you sample among the dimension of each vectors. This kind of priors is actually has proved to be the more efficient. We don't really know why, and that's the one that is used by all the tabular foundation models today. So the second pillar is the architecture itself. So how do we actually implement the model? So all models are in context learners, as I said, and they are implemented as pre-trained transformers. Several ideas have been proposed the last 2 years to optimize how we implement this model, but basically we don't see like a huge difference of performance between all implementation. The main thing that brings the architectures is what will be my constraints when I'm gonna scale my model to very large tables. The first model that has been introduced was TFM v1. It was the initial paper from 2022. The idea was very simple. So for each dataset, each rows are tokenized by a linear projection into the latent space. And you trained a simple standard transformer over the sequence of tokens that you get. So for the context, you encode both the target and the row. And for the query set, you only encode the row. So it was a model that was pre-trained exclusively in synthetic datasets. And it was the first model to beat tree-based model on small tables. But still, it was a great effort. The second version of TFM introduced 2 main modifications that are still applied today in actual TFMs. The first one is instead of tokenizing all the samples, you tokenize each cell. So each cell becomes a vector in your latent space. And thanks to that, you can apply transformer in 2 directions. You can apply a transformer within the direction of the row and within the direction of the columns. And that enables to catch way more patterns in the distribution and to better encode the semantic of each column. And this first model, which was very lightweight because it was only 7 million parameters, was the first TFM to beat tree-based model on very broad academic benchmark. Today's TFM are all converging to these architectures, which was proposed by a French team, a French academic team. Their idea was to decompose the TFM architectures into 3 stages. The first stage is a column transformer that embeds efficiently the column semantic. The second stage is a row transformer that tries to compress the column dimension, so that enables to create a latent space of the table. And the last stage is the ICL block, so that's the TFM v1 over this latent stage that has been trained in the row transformer. This compression enables to reduce drastically the complexity of the architectures and to scale it better. And it has been trained on curriculum learning over different size of tables. And as I said, the funny thing is that all TFMs today are converging to these architectures. And the last pillars is a bit underexplored, is the context that you use at inference time. So we know that in a lot of cases, the way you handle your context, so the samples that you present at your model with the labels, it has a huge influence of the model. So when you say that, the first thing that you think is, oh, that's great, we can create like efficient sampler of context to optimize memory use and make my model scale better. but actually that's a very hard subject. Some models like TabDPT try to optimize context only for performance. Anyway, that's a bit of a new way of handling tabular data. I think that context sampling is a bit like asking the question how to efficiently prompt my TFM. And that's also a new explainability direction because it can enable to better understand how a TFM works beyond feature attribution. So as said, a lot of time that TFMs were outperforming tree-based model. To highlight this point, I can present you the results of a very large-scale tabular benchmark that we are releasing soon. So that's the comparison of performance of tabular foundation model on 200 classification tabular datasets. And that's the only tabular benchmark that has so many datasets and so many tabular foundation models. The first thing that is very interesting is that, as you can see, there is 7. So the 7 first models are TFMs. So there is a huge gap between TFMs and tree-based models. The second thing very interesting is that, as you can see, the best tree-based model is very far away from the TFM family. And the third thing that is very interesting is that there is a convergence of the TFM. So there is a top 3 TFMs actually that are out. Typical V2 Seldon, which is our model, and TAPFN V3. And so that's a critical ranking diagram. So lower is better. And when you see little line, it means that it's not, the difference is not statistically significant. One thing still very interesting is that you see that TFMs and tree-based models are really separated in this diagram, which show that there is 2 performance regimes. Of course, there is one huge drawback of using TFMs is that it's quite expensive to run because it has to run on GPU and it consumes a lot of memory, so it can take a lot of time. And it can be very hard to use it at scale on very large data. So that's why we offer a very efficient API that has no data volume limits and that is quite fast and that follows all the scikit-learn conventions. So there is no code overhead to use it. So yeah, you can visit our documentation and platform. It's very easy to use. To conclude about TFMs, I think that we show that TFMs work, but obviously they don't solve everything yet. So there is a lot of things that remains to explore and remains to do. And that's what we are doing at Neuralk. So if we come back to our 3 pillars, there is a lot of open questions, which are open research questions about the prior. So we don't know actually how to define the prior quality. We don't know how to generate more realistic priors or even how to guide the training of the model thanks to this prior. With respect to the architectures, current models actually applied in a very brutal way transformer to tabular data. There is a lot to do to like encode more efficiently the tabular nature of the data. And of course, there is a very open question, which is very interesting, is that we saw that there is a true predictive power behind tabular foundation model. And I think it's totally an open question to know how we can fuse this predictive power with current reasoning capacity of LLMs. And finally, yeah, like I said, the context is a bit underexplored currently, but I think it's a great area to find new way to explain TFMs and to bring more trust in the prediction that are outputted by these models. Thank you for your attention. So 3 things to take home with you. You can try our API. We have some free credit for you. You can check out our benchmark. And of course, we are hiring currently in Paris and London, mostly in research teams. So If any of the stuff that I talk about is resonating with you, come talk. Thank you.